We've talked about different kinds of solids. Crystalline solids are those that have long-range order to their particles. And we often see beautiful shapes on the macroscopic scale where, these things are large enough that we can see. This is some sort of an ionic crystal. It reminds me of Superman's ice cave, right? Anyway, beautiful crystals here. This was not carved. These crystals grow, and they naturally grow that way because it's a crystalline solid. This is a close-up view of a snowflake. When water freezes, it makes a crystalline solid and makes some very, very beautiful designs. We can determine the structure or how those particles are arranged using X-ray crystallography. So we've learned before that electromagnetic waves can interfere with each other. So if we get two waves that are in phase, they can interfere constructively and cause the amplitude to become larger. And two waves that are out of phase will destructively interfere and cancel each other out. And we looked at how light passing through two slits, which has a distance similar to the wavelength, produces an interference pattern. We looked at this when we talked about the wave-particle nature of electrons, and how the electrons passing through two slits also caused an interference pattern, unless you stuck a laser there to see which slit the electron was going through. And then it quit behaving like a wave and started acting like a particle. So we can use this idea of interference to study the crystals. So the atoms inside these crystals have spacings of about 100 picometers, and that is similar to the wavelength of X-rays. So when we pass X-rays through this crystal, the lattice here acts as slits for the X-rays passing through, and because the distances between these particles are similar to the wavelengths of the X-rays, we get diffraction patterns. And those patterns allow us to figure out the spacing between the planes of the atoms. So here we have a crystal, and you see there's a plane here of 5 blue atoms, and then there's another layer here with 3 red atoms, and then another one with 5 blue ones. So there are 3 planes here. And the distance between the planes, those little gaps, act as slits and can cause interference from the X-rays. And so it's a little hard to see. There's little dots. There's little white dots all over this black. It almost looks like what's that toy with the little pegs? Light bright. It reminds me of a light bright, where this is the black paper, and you took all the pegs out, and there's just little holes with light coming through. Does everybody know what a light bright is?
Yes.
Okay, because I know that was a while ago, but it's a cool toy, except for all those stupid pieces. And that's why your mother got rid of it, because she was tired of the little pieces all over the floor. So how does this work? Well, here we have 2 different rays. Two waves in phase have constructive interference if the difference in path length is an integral number of wavelengths. So here's ray 1 coming in. Sorry, pointing the wrong one. Ray 1 comes in, hits this atom, and bounces off. So that's the path length that we're comparing ray 2 to. So ray 2 comes in and hits down here and bounces off. This ray traveled farther. How much farther? Well, this little distance here and that little distance there. That's how much farther it passed. And so the distance, the difference in distance, oh good grief. Here's the wavelength, and this is an integral number, n, so some integer. So we need some multiple of the wavelength to equal 2a. This will cause constructive interference. So if the distance that this travels in addition to the distance that the other one travels is 1 wavelength longer, or 2 wavelengths longer, or 17 wavelengths longer, the rays will still be in phase when they come out. Does that make sense? So maybe a little bit like a marching band. If they're marching in step and all of their steps are the same length, going around a corner doesn't work very well, does it? People get out of step. They can't be next to each other and be in step at the same time. Unless you go just the right distance farther and come over this way, you can be still in step. So in order for these two waves to remain in phase, this distance here has to equal some multiple of the wavelength. Question?
Yeah, integral number. What exactly?
An integral number is an integer.
I thought it like integrate.
No, integrating. No calculus. No calculus. Yeah, integer is a noun. It's a whole number, right? 1, 2, 3, 4, 5. Integral number becomes an adjective. It describes the word number. So that's all it is. That's a good question, because I bet everybody else was thinking the same thing. So you can do a little geometry here, looking at these angles. We call this angle theta, and so you can get the relationship between the sides of that triangle. And the bottom line is what's known as Bragg's law. So n lambda, where lambda is the wavelength, equals 2d sine of theta. And theta is the angle at which you're shining these rays onto this substance. And so the experimenter controls theta. You set the instrument so that it's shining these X-rays at an angle. And what you do is you vary the angle. And you look for places where you get constructive interference. That shows up as bright spots. And so when we have constructive interference and we know the sine, we know theta, we can find the sine of it. And the distance here, it's got to be labeled on here somewhere. The distance, yeah, it's right there, is the distance between these two planes of atoms. And so we can figure that out by knowing the wavelength and knowing what this angle is. Did that make any sense at all? Yeah. It's really, really cool. There's a lot of math and geometry involved. But this is how they determine what kind of a structure different crystals have. And this technique was a very important part of figuring out the shape of the DNA molecule, because they were able to use X-ray crystallography to establish, that's what led to the discovery of the double helix of DNA. Any questions? X-ray diffraction, yeah, that's another name for X-ray crystallography.
Oh.
Yeah, because we're diffracting the X-rays. That's good. I didn't think about that. So typically what we do is we measure what angle produces the interference, and then we rearrange that equation like this. So the distance between the layers equals some integer number times the wavelength, which we know, divided by 2 times the sine of theta, the angle at which those rays are being shown, blasted onto there. You see, I always get ahead of myself. So it's great for determining simple atomic lattices, like the structures of different metals or atomic solids. It can do proteins, and we can also do DNA and other important molecules, and have an understanding of how they're organized at the particle level. It's very cool. Okay, so here's an example. The spacing between layers of molybdenum atoms is 157 picometers. What are molybdenum atoms? Okay, molybdenum, which is really hard to say, molybdenum is an element. It's an element. Molybdenum, where did you go? I'm pretty sure it's MO. 42? We don't use it much, do we? Yeah, I'm pretty sure 42. Next to niobium and technetium. It's a metal. Molybdenum. There's an ion molybdate. It does what most metals do. Makes cations. It's ductile, malleable, most likely. Do we use it for anything? I don't know. That would be a good question for Google. Or Siri. You can get poisoned from anything. Okay, we've had this discussion before. Anything can poison you. Oxygen, water, anything. Okay? Maybe even love, but love isn't a substance. It can be toxic love. So the spacing is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. Well, we're going to need that equation. So let's go back and look at it. They're asking us to calculate the angle, which is theta, so we probably don't want to use this one. Bragg's law would probably be easier to rearrange. So n lambda equals 2d sine theta. Let's see if I can remember that long enough to write it down. N lambda equals 2d sine of theta. So lambda is the wavelength of the X-rays. What is the value of that here? – 154 picometers. It doesn't come out and say wavelength, but it says 154 picometer X-rays. That means that's the wavelength. The spacing between layers is 157. What letter corresponds to the spacing between layers? Say it louder, I didn't hear you. D, thank you. And then we're told that n equals 1. So we're supposed to find theta. So we're going to have to rearrange this, aren't we? We want to get sine of theta by itself, so we'll divide both sides by 2d. And I'm just going to flip it around. Now we have sine of theta equals n lambda over 2d. How do we undo sine? Inverse sine, right? So what we're going to do is we're going to plug these numbers in, calculate what sine of theta is, and then use the calculator to do the inverse sine. So n is 1, and lambda is 154 picometers, and 2 is 2, and d is 157 picometers. So the units of the distance in lambda, the wavelength, cancel out. So it doesn't matter what unit you have here as long as they're the same. And I left my calculator in my bag. Okay, I need to get it in my calculator. 154 divided by 2 divided by 157. So 0.49. 0.44586. Does that have any units? No, it doesn't. And so now I'm going to do the inverse sine. So that's going to, on the calculator, it looks like sine to the minus 1 of that number. I don't want to write it out. So second, there we go. 29.37. Actually, let's go with 29.4. What unit should I put on that? You got a different number? Are you in radians? So 0.4904 inverse sine.
Would that be degrees or?
I believe that, well, it depends on how your calculator's set up. Mine's set up for degrees. So I believe it would be degrees, 29.4 degrees.
So the unit.
Degrees. Mhm. So, if this is the surface that we're blasting, then the X-rays, that's 90, this is 45, and so the X-rays are going to be coming in, something like that. This angle is going to be 29.4. So when you come in at that angle, you get constructive interference of the X-rays. Because as the X-rays strike the solid at different places, the one X-ray bounces off the top layer, another bounces off the second layer, another off the third layer, and because the difference in distance that they're traveling is an integral number of the wavelengths, then they end up constructively interfering, and we can observe that. It's very cool. Any questions?